Hello, 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 and welcome back to another video from Alex's Calculus Corner. And today, as you can see by my picture here, to be or not to be continuous. And then here's a little Shakespeare pondering whether that function is continuous or not. So the main arching idea today will be continuity. And let's get right into it. Let me dismantle my little drawing here. Alright, so there are three different types of discontinuities that occur. The first is the infinite discontinuity, which is something such as 1 over x, or something with some sort of asymptote, where it would go like this. And it will never reach that point 0 because of this infinite discontinuity. The second example is a jump discontinuity, which would be something like this. If you had a line going this way, and then it skips right above here, which would be done usually by a piecewise function. And then the third type is a point discontinuity, which would be a line here and say one singular point where this line does not exist. The open circle meaning the point does not exist there. And so these are classified into two different ways, removable and non-removable. So looking at these, what would you think is removable versus non-removable? So looking at this infinite function here, does this look removable just based off of intuition? Well, no, because it is an infinite line that separates these two. So this is a non-removable. Then this here, well, this is just a whole mess. I don't know how we'd even think about getting this into one continuous function without creating our own. This is also non-removable. And then this last one here, just a singular point. Taking this point out makes it into a continuous function. So this is called a removable discontinuity. And so those are the three main types of discontinuities. Alright, and now let's get into things being, let's get my pen thickness right here, things being continuous. So there are three rules that need to be met in order for a function to be called continuous. The first rule is that at some value c, where x equals c, the function is defined. And so it exists. It's there. Right? The second, let me just edit this a little bit. The second is, the second would be that the limit, like we talked about in the last video, the limit as the value c, as x approaches the value c from the left, which we denote by this little negative sign above here, or actually it would be, that the limit as x approaches c from the left equals the limit as x approaches c from the right. And the third and final rule is that these two values here are equal to that value of f of c that we defined in the first part. So those are the three main rules to decide if something is continuous or not. Alright, and let's go over some other overarching knowledge. So, any polynomial is continuous. Because there are no values where a polynomial such as just x squared, we could do x to the third plus x squared plus 2x plus 7, that these are not defined and have a discontinuous part. These are always continuous and smooth functions. So that's one idea. Another idea is the idea that we looked at earlier about when we talked about different types of discontinuity, we talked about the infinite discontinuity, where there's an asymptote present here. So this asymptote is decided by the equation. So for example, here for the graph of 1 over x, which is right here, we see that any value where x equals 0, this is the value. Therefore, we know from looking at our limits that when the limit as x approaches 0 for 1 over x, this does not exist. Therefore, it is not continuous at that point, and it is also non-removable because this value will never exist. Which, since it's this 1 over x value here, we know that we can call it a line x equals 0 because it's a sole x here in this bottom. This line x equals 0 is what decides our asymptote and what this function will never hit and where the discontinuity is. Alright, and let's start with a small example that showcases this infinite discontinuity. So let's take the function x plus 5 divided by x plus 5 multiplied by x minus 2. Right, so looking at the rules of discontinuity, we will check to see if this function is continuous or not. But we will also evaluate what type of discontinuities it could have just based off of the function itself. So here we see right away that these two x plus 5s can cancel out. But when you cancel these x plus 5s out, you need to denote that at that point x plus 5, or at that point that makes this 0, that there's a hole, and that there is something that will make the function 0, or make the function not exist. Because if we see here, so if we take this x plus 5 out, what value of x will make this 0? -5, right? So if we plug -5 back into the original equation here, we get 0 over 0, which we know does not work, which also gives us a hole at that point where x equals -5 in this function. And then along with that, I will just erase this little bit of work here. So we know there's a hole at an x equals -5. And we also see here, once you simplify this expression, it becomes 1 over x minus 2. And we saw in the last example with 1 over x that we used x equals 0 as our asymptote value. But here, we're going to be using x minus 2 equals 0 to find what line is denoting our asymptote this time, which we can see is x equals 2. So on that second notch, this is where our asymptote is present for the graph. So we see here that this has an asymptote at x equals -2, or x equals +2, pardon. Alright. Let's see what else we can do here. So another common way to discuss whether a function is continuous or not is to have two piecewise functions that make a singular function. And this is a common way of testing knowledge of continuity, because they are two separate functions, and in order to be continuous, they have to equal each other at the point that you're testing them for. So for this example, let's do it in blue here. The piecewise function of x squared on values of x less than 3 and 6x minus 9 on values of x greater than and equal to 3. So let's think about the steps here. So this will be denoted as f of x. Let's think about the steps here. Step 1. And we're doing this, evaluating this at x equals 3. Is f of 3 defined? Let's see. So f of 3, what would we use here? Would we use this? No, because since it does not have the equals to sign underneath, the 3 is not included within the x squared part of the function. So we use this bottom part here of 6x minus 9. So we know here, 6x minus 9, we do 6 multiplied by 3 minus 9, which equals 9, because this is 18 minus 9. And then let's go to the second step. The second step is the limit as x approaches, and in this case we're using 3 from the left of this function f of x equals the limit as x approaches 3 from the right of this function. And for piecewise functions, this is why these are useful. This is why that we can do this sort of step with some certainty with piecewise functions, because we can see here, since we're evaluating at the point x equals 3, this top function here is for values less than 3. So we know that it is coming from the left. If we look at the xy axis, it is coming from this left side of 3. So we know that this top equation is approaching from the left. So we use that for our first expression. And using that here, we can plug in 3 to the limit, which becomes 3 squared, which comes out to 9. And on the bottom here, that is approaching from the right, because and including the value, since it has the equal to sign here. So we use that top equation, and since we solved up here, we also know the value is 9. But even if we re-plug in that value of 3, we get 9 as well. So this second step is now checked off. And now the third and final step, we need to check that this value from the top is equal to these limits from the bottom. And if we check that here, we have 9 here, 9 here, 9 here, 9 equals 9. That is satisfied. So we know now that since this function has passed all of these steps, that it is continuous. Let's do one more example with the removable discontinuities. So with the function x plus 2 divided by x squared minus 4. So let's evaluate this. If we expand the bottom, we get x plus 2 over x plus 2, x minus 2. And we can see here that we can cancel out these x plus 2's. But we know when we cancel out these x plus 2's, we have to account for that in this case, with this equation, if x was equal to negative 2, our expression would have been undefined. Therefore, we know that there is a hole at that value of negative 2. We also see here on x, one on x minus 2, that this x minus 2 will not exist, or this denominator will not exist, or this whole function for that matter will not exist when it equals 1 over 0, and that will come when x equals 2. Therefore, we know that any value where x equals 2 cannot exist. So there is that asymptote again. And that is all I have. So thank you for listening again and watching to a small discussion on continuity and how they relate to limits like we did before. And make sure you always remember, let's do a different color, to be or not to be continuous.